Now let us talk about decidability. So we are going to say decidable, undecidable and semi-decidable. What does it mean? Before understanding that, first of all you should understand a property. Property is nothing but a behavior. Generally it is about strings. We are talking about strings because in entire your TOC we talk about strings, right? Now a property of strings is said to be decidable, said to be semi-decidable, said to be undecidable. When? For that you should understand first of all details of property. Example, tell me one property. String in the form of WW is a property. Here property is nothing but being in the form of WW. Let's collect them. Okay. So here property is nothing but this one, WW form. Let's collect all such strings x1, x2, x3. Whenever this property is satisfied, you collect it. Okay. When you collect all possible strings, then it forms what? Definitely a language, because we know that language is nothing but collection of strings. Okay. Now focus on this bag. Now come to machines. Now I have a Turing machine, especially total Turing machine. What it is doing is, if I give any random input, let's take something W. If I give input W, don't get confused between this W and this WW, different. Now it is going to say yes, that means it is accepting sometimes, it is rejecting sometimes. We know the property of total Turing machine. Definitely it has to do yes and accept and reject, correct? Let's use accept only, accept and reject. Now example, let's say this total Turing machine is designed such a way that whenever you give input W, if that W is part of this bag, if this W is a part of this bag means the string has this property, then it is accepting. Try to understand the connection between property and this total Turing machine. Whenever a given input is having a property P, it is accepting, otherwise it is rejecting. Then such total Turing machine if you have, then we say that such language is decidable, otherwise such property is decidable. Here property is nothing but language, right? So finally decidability is that, right? Recall again. When you have a, let's say you are collecting all the strings which are having a property, okay, they form a language. So here I use language and property interchangeable. Having a property, otherwise having a language, same, okay, for me. So such language is accepted by some total Turing machine, then we say that it is decidable, which is language. That language is decidable. Now what is semi-decidable? Same problem. Example, let's take another property. Let's say you have a property that is being in the form of a power n, b power n. So this is your property. Now collect all strings which are in this form, a power n, b power n. Okay. Example, a, b, b, a, b, a cube, b cube, in that way. So collect all such strings. It forms what? A language. We know that language is nothing but a language in the form of a power n, b power n. So here property is nothing but being in this form, and this is the language. That is the relation between property and language. So property and language are almost same, right? They can be used interchangeably. Now such language is called semi-decidable if you can show Turing machine for that. What kind of Turing machine we have to show? If I say that this is a Turing machine for this property, that means if some input is given, it should accept whenever that input is in the form of a power n, b power n, because that is a property. Otherwise you can loop, otherwise reject, not a problem. Such a machine if you have, I don't bother if you loop, I don't have any problem. But whenever the input satisfies the property, you should accept it. Such a Turing machine if you can show, then we say that such language is semi-decidable. That is a fundamental definition of semi-decidability. Now finally you understand what is decidability, what is semi-decidability. For any property, if you show a total Turing machine, then that is decidable property. For any property or a language for that property, is for that if you show to just Turing machine, I don't know whether it is a total Turing machine or not, but if you show a Turing machine, then that property is called semi-decidable. Okay. Now one more thing is undecidable. So a property is called undecidable, then there is no total Turing machine for such problem. Okay. So we know that problem is nothing but a language now, right? So for a language, if there is no total Turing machine, then we say that is undecidable. Simply Decidable is quite opposite to undecidability, correct? If something is not decidable, then it is undecidable. Okay. Now let's summarize decidability, semi-decidability and undecidability. If a problem has a total Turing machine, that is decidable problem. If a problem has just Turing machine, I don't know anything else, then that is semi-decidable. It might have total Turing machine also, I don't know, but definitely I got one Turing machine, then that problem is semi-decidable. Now third one, there is a problem which doesn't have any total Turing machine, then that is undecidable. Okay, if it has this total Turing machine, that is decidable. If it doesn't have, then that is undecidable property. So blindly remember, any property is not decidable, that is undecidable. Okay, let us talk about universal Turing machine. To understand universal Turing machine, first of all you should understand what is the encoding of Turing machine. I will tell you what is encoding of Turing machine. You have a Turing machine. Having Turing machine is nothing but having description of Turing machine. That means what is your set of states, and what is start state, what is the reject state in your machine, and what is the transition function. That details is called your description of the Turing machine. Now given a description, we have to convert that into encoding. I will show you how to encoding, especially let's focus on binary encoding. And one more thing, exact encoding scheme is not really important, but you should know that yes, we can do binary encoding. If you know that, that is sufficient. So let me show details of encoding in a Waze way. That means not in an unclear way, not in exact way, because exact details are not really required. So let's take one simple example. Let's say you have a Turing machine. Tell me some important details which I want to encode. So input alphabet, correct? Let's say your input alphabet is A comma B, and the states are, let's say there are 4 states. They are, let's say, start state, some reject state, some final state, and one more state. Let's take that state as Q. These are all the states. Now I am just representing your Turing machine. I am writing the description of your Turing machine. States, input alphabet. What is tape alphabet? Let's say this is states. Input symbols, tape symbols. Let's say tape symbols are A. That means tape symbols are symbols which you can write on tape. Input symbols are part of tape, that you should understand. A comma B comma X comma Y, let's say. So this is called description of your Turing machine. And what else? Some transition function, correct? So we'll see transition function later, and after that we know that there will be a left hand marker. After that, some extra stuff, right? They are all not so important, because I would like to show only important details. Let's say these are all essential details of your Turing machine. I'm going to encode them. Example, let's say your states are S comma R comma T comma Q. Let me number them. I give numbers like this. S means 0, R means 1, T means 2, Q means 3. It is an arbitrary association. You can try anyway. Next, you have tape symbols, right? Let me cover tape symbols. The tape symbols are A comma B comma X comma Y. For first 2 are, let's say, input symbols, right? For A I give a number 0, for B I give a number 1, and for X I give a number 2, Y means 3. In that way, so by these numbers I can understand that this is one symbol, this is one symbol, 3 means one symbol, 2 means one symbol. You will understand slowly. At this moment, let me number like that. Now I am going to write this kind of binary format that is going to represent exactly the same thing. How you see? First I write number of states. How many states you have? 4, right? Then I write like this, 0 power 4. So whenever someone reads this one, they understand that, oh, there are 4 states. And what are they? Simple. That 4 are by default 0, 1, 2, 3. In my encoding, you see that 4 states are 0, 1, 2, 3. Agree? In that way, I can uniquely represent number of states and various state information. Now we represent tape symbols. So we have 4 symbols, right? That's why we encode like this, 0 power 4. Okay. Now, out of them, how many are input symbols? 2, right? That's why we write 0 power 2. In that way, so this 1 is going to be working like a separation. So this number of zeros represents states. This number of zeros represents number of tape symbols. These number of zeros are going to represent your input number of inputs, correct? Now in that way, remaining stuff. So when you encode like this, everyone can understand in a unique way, correct? If you fix the rules and if we have a common agreement, whatever the way I write, in the same way if you encode, then easily we can understand that. Let's say 0 power 4. 4 is nothing but, see now how I decode it, I will tell you. 4, first zeros represents number of states, 4. What are they? Automatically they should be 0, 1, 2, 3. Such a way I encoded them. Next, 0 power 4 indicates in tape symbols. We have 4 tape symbols. What are they? 0, 1, 2, 3. Okay, see, that's why I gave A0, B1, X2, Y3. Now next, 0 power 2. That means this represents number of input symbols 2. What are they? 0, 1. Yes or no? You check it out. A0, B1. In that way, we can uniquely encode it. That means Turing machine can be encoded. Now one more thing is how to represent, otherwise how to encode the transition function. That is a final thing, right? Example, you have a description like this. Transition function. Let me take one state, Q, okay? Q on something, otherwise I take start state. Start state on seeing input A. Generally we write like this, right? S on A, you go to Q and make it B and go to right side. How to encode it? For that what I do is, I am going to use zeros and ones and I am going to do the same thing. First of all, blindly write like this. 0 power S, stop, A. 0 power A, stop, Q, B, R. We know that any transition function will have 5 components, right? S, I mean state, symbol, direction, correct? That's why 0 power S, 1, 0 power A, 0 power Q, 1, 0 power B, 1, 0 power R. Okay, so let me use L means 0, R means 1. This is the encoding for directions. Okay, let's do that. Otherwise I use L means 1, R means 2. Anything we can use, not a problem. Now you see how we are going to encode this kind of descriptions. We'll see. Whenever you have a description, write 0 power S. S is what? 0. Write 0 power 0. Okay. Now 1. Next 0 power A. What is A here? See, A is nothing but for us 0 power 0. This is for your convenience, but finally end of the day this will be converted like this. 0 power 0, 1, 0 power 0, 1, 0 power Q. Q means what? 3. 0 cube, 1, 0 power B. B means what? See, 1. 1, 0 power R. R means 2, 0 square. In that way, I am going to encode all your description, otherwise transition function. Finally, all your Turing machine description is converted to encoding binary format. So you realize that a Turing machine can be converted to zeros and ones. Once you convert the Turing machine into zeros and ones, if you know the alignment, that means if you know how this conversion, otherwise how this encoding happened, then exactly the same way if you decode it, we can understand the functionality of the Turing machine. Agree? Now if you see, by reading this one, I understood that there are 4 states, 4 tape symbols and 2 input symbols, and by seeing this one, 0 power SC, S on A will go to Q and the symbol modification is B and it will go to right. Here also I can understand the same with binary encoding also. Finally, we are not disturbing the meaning of the Turing machine and we are converting that Turing machine into binary format. So once we have a binary format, then we are going to learn universal Turing machine. Okay, so let's try to understand universal Turing machine with this terminology, with Turing machine encodings. From now onwards, everyone who is watching my videos, imagine that every Turing machine is nothing but a binary format, correct? Zeros and ones. Now all collection of Turing machines is nothing but a language. Wonderful, isn't it? So every Turing machine is nothing but what? A string. Remember it. Turing machine is a string with zeros and ones from now onwards. So all possible Turing machines in the world, if I take into a bag, that bag is nothing but collection of strings, correct? So in that way we can understand about collection of Turing machines. Okay, that forms a language. Remember it. So now we will go to universal Turing machine. Sir, what is universal Turing machine? I am going to explain. That is one of the Turing machine. What is the functionality of Turing machine? We will see. So it's like a compiler kind of thing. Okay. Generally your compiler, otherwise interpreter, does what? They take your program, and they simulate it, right? That means they understand your program and exactly, so they convert that program into another program. Of course, that is a job of compiler or interpreter. In the same way, this universal Turing machine is going to behave like, exactly like any of the Turing machine. We will see the details at this moment. Within one line I cannot tell that, but I'm going to give complete description of your universal Turing machine and its functionality. After that you can understand it. Let me begin with universal Turing machine. Let us see this Turing machine. So first of all, I take some pattern m hash x. What is that, sir? M is nothing but a binary format. Okay, what is hash? Hash is a just symbol which separates m and x. What is x, sir? X is a binary format. Can you explain us very clearly what does it mean, m hash x? M hash x is nothing but this kind of binary formats, 0010 hash 010. Hash is just used to separate one binary pattern with from another binary pattern. Sir, why are you doing that? So here what we are going to assume is this first pattern is representing one Turing machine code. Sir, how Turing machine can be represented as binary format? Don't ask me, because already I taught you how to encode a Turing machine into binary format. Assume that for simplicity this is one of the binary format of a Turing machine. That means otherwise it is a Turing machine code in a binary format, one of the encoding. 010 is one of the input which we can give for a Turing machine. Okay, such a input it is. We know that Turing machine takes input, right? So 010 is one of such input. Now I am going to design universal Turing machine. It's a very big Turing machine. That's why I can't give a code for it. Example, if you ask me, sir, please explain us operating system code. How can I explain in 5 minutes? Rather than that, we generally discuss about functionalities of operating system and just ideas of operating system, right? In the same way, here also I am going to teach you functionality of universal Turing machine. It is very big Turing machine, so that its code is very complex. Rather than that, we understand what that code will do. Okay, now we will see. Assume that, let's say, universal Turing machine is having some code. Because of that code, it is going to do some functionality. What is that? I will tell you. For that universal Turing machine, we are going to give input in this kind of format. Okay, what is that? M hash x. Universal Turing machine accepts only this kind of code. Sir, what if I give different code? How you give? Like this, sir, 01011 followed by 0111. I don't give hash. So your universal Turing machine is having a code such a way that it will do one scan and it can find out whether there is a hash in between that or not. If there is no hash in your input, it will simply reject it. Okay, that means your universal Turing machine is going to reject inputs in the form which are not in the form of m hash x. Okay, binary format hash x. So that will be rejected. Don't worry about it. That is one of the functionality of your universal Turing machine. Already I told you one thing. Your Turing machine can be designed. That means we know that Turing machine can be designed such a way that given input, whether that input contains hash or not, it can check it out. Correct? Did you remember what were the functionalities you have seen for any Turing machine? We have seen a Turing machine which accepts a power n, b power n, which can copy the input from one place to another place. Similarly, your Turing machine can do lot more things. Okay, remember it. Similarly, one of the things your Turing machine can do is whether your input has hash or not. That's quite easy. So there will be a state. So I'm just telling the functionality how to do that. Simply take every symbol. If it is not hash, go right. Not hash, go right, in that way. If you don't see any hash, go to reject state. In that way, easily we can develop that functionality. So universal Turing machine is going to have very complex code. First, it will check for hash. You should agree that things. Okay, so at this moment, whoever is watching my video, don't try to write a code for universal Turing machine. It's like writing a operating system code while attending the OS lecture. Is it possible? No, right? It needs lot of patience and lot of details. But understanding operating system, everyone can do, correct? So we can understand easily. But writing a rigorous code will be definitely difficult at this moment. Similarly, understand the functionality of universal Turing machine. Just listen. One functionality is, first it will check whether the binary pattern has hash or not. If there is no hash, then it will reject it, because I don't want that kind of inputs. Okay, sir, please tell us what it accepts. I'm telling. So whatever the input, if you give right input, example, let's say a proper input is given. Okay, like 0010 hash 010. Rather than writing binary formats, we write like this, m hash x. Okay, now Why, sir? Why don't you write binary? Because this binary format has a meaning. I will tell you what is that. So generally your Turing machine is going to check whether if this first pattern is a Turing machine code, really it is a Turing machine code, and if X is an input, so your universal Turing machine is going to run this Turing machine code on X. How it will do, I will tell you. First of all, assume that at this moment m hash x is simple random binary format. Okay. Now what happens? Your universal Turing machine copy m hash x here, m here, x here, and it will begin with starting state. Okay. So yes, your universal Turing machine will have a code such a way that input will be copied into multiple tapes. Okay. Otherwise, assume that these are all multiple tracks. Track 1, track 2, track 3. Okay. For that you need a very lengthy code, I know, right? But that's why understand the meaning of the code. Your universal Turing machine's code will be such a way that your input will be copied here, m will be copied here, x will be copied here, and it will start simulating with the starting state of your Turing machine m. Initially your universal Turing machine will read the code of Turing machine m, and because we know the code of m, we know the start state of that one. Okay, and we mark it. So now at this moment, so after some point of time, this will be the snapshot of your universal Turing machine. Universal Turing machine is now about to simulate m on x. Example, how it simulates, I will tell you. There will be definitely in your in your code m, there will be an instruction like this, right? S on A, go to Q, comma B, comma right. Okay. But in a binary format. Assume that we know what is the structure of binary format. Easily we can understand that, we can understand as a human being, you are understanding this, right? As a Turing machine code, so this universal Turing machine can understand the alignment and it can catch this point. It will read like this. So where is S? Yes. What is the next symbol? A. S on A, what it is doing? Q. Through its code, it will understand that the next state is Q. Okay. Now let me elaborate this x. X is actually, let's say, ABA input. Though I am showing in English alphabet, but actually it is binary. Don't ask me at any time, sir, why are you writing ABA? It should be binary format, right? Yes, let's say it's a binary format. But I'm just telling you the high level description of universal Turing machine. Now see, S on A, it goes to Q, then your universal Turing machine finally remembers it. Okay, then after that what we have to do? We have to change it to B. Then what your Turing machine will do is it will change like this, B. Then after that we are going right. Then your universal Turing machine marks it. Why? Because next time we have to read this symbol, correct? We have read this symbol. Next we have to read this symbol. That's why it will mark it. After that it will keep quiet. Then it will start simulating the next step of your Turing machine M. How, sir? It will scan the Turing machine code again. There will be, and it will look for a pattern Q. Whenever there is a pattern Q, okay, and whenever there is a pattern like B, then it will try to understand it and it will see the next state. Example, that is R, and let's say symbol B is B and it is going to right. Then what your universal Turing machine is doing, I will tell you. Q on B, R, it will note it through its code. Understand? Okay, such a way your universal Turing machine's code is designed. Though I am explaining in a very lengthy way, but because I'm going to teach you a lot of details here. Okay, but after end of the session I will summarize everything, don't worry. So then what to do? After writing R, we have to go right? This is right symbol, sorry, R. That means the next input we have to scan is this one, then put a mark like this. For that there will be very lengthy code. There is a lengthy code in universal Turing machine. I'm not showing it, but I'm explaining how that, what is the functionality of that code. After that it will, did it modify this input symbol? No, that's why B is B. After that state is R. Then it will go to the next step. In that way, finally what this universal Turing machine is doing? Universal Turing machine is simulating the code of this Turing machine M. Okay, sir. Finally what it will do, sir, after simulation? Example, after whenever this Turing machine, example, let's say after some point of time, let's say your Turing machine, I'm talking about M. Your Turing machine M comes to final state T, then your universal Turing machine will stop the execution and it will say I am also final. Okay, At any point of time, if you are after simulation of your Turing machine M, if the Turing machine comes to reject state, then your final universal Turing machine also comes to reject state. Sir, what if your Turing machine M, which you have binary form, if that is in loop, what your universal Turing machine is going to do? We don't have any clue. We also will be busy simulating that Turing machine and we will be in loop. So let's try to understand the final behavior of universal Turing machine. Okay, let's summarize. So your universal Turing machine is having a functionality such a way that it will take input m hash x, correct? After that it is running m on x, it is running x on Turing machine M, correct? Okay, if m accepts x after simulation, your universal Turing machine is simulating m on x. If m accepts x, what your universal Turing machine is doing? It is coming to final state. That means what? If m accepts x, then m hash x is the input for your universal Turing machine. So your universal Turing machine is going to accept. Okay, yes, m accepts x, then m hash x is accepted by universal Turing machine, remember it. Next, sir, if m rejects x, really m rejects x, such a Turing machine is m, then m hash x is rejected by your universal Turing machine. That is the behavior of universal Turing machine. Sir, if m loops on x, then your universal Turing machine is also going to loop, right? Then on m hash x, universal Turing machine loops. That is the summary of universal Turing machine. Very simple. It takes input m hash x. If m accepts x, universal Turing machine accepts it. If m rejects x, then universal Turing machine rejects m hash x. If m loops on x, then your universal Turing machine is going to loop. That is about functionality of universal Turing machine. Remember it. Now question, what is the language accepted by universal Turing machine? Sir, I want to know the language accepted by universal Turing machine. Very simple. Go to accept state. When it is accepting this line, you read this line, because this is about rejection. We don't bother about rejection. What it accepts? Your universal Turing machine accepts m hash x patterns whenever m Turing machine accepts x. See, if m accepts x, then m hash x is accepted by universal Turing machine. Now let me show a bag. This is the bag of strings, all m hash x, m1 hash x1, m2 hash x2. This kind of all these patterns forms a bag. Okay, so this bag is accepted by all these strings are accepted by universal Turing machine if and only if m1 accepts x1, m2 accepts x2, m3 accepts x3. Such a language is universal Turing machine. Okay, now let me write in a clear form. Okay, we have seen universal Turing machine, right? Now what we do is we do the same thing. That means we try to understand the things with language form. Example, this is a language. Generally we describe a language like this, right? What kind of language it is? First we see. It is nothing but it is a collection of strings. Yes, so I'm talking about this one. Yeah, what kind of strings? Any strings, they should have hash and some binary format m, some binary format x. Is it enough? No, there is a condition. What is that? If it is a Turing machine code m and m is a Turing machine code and x is input on this Turing machine, if this input x is accepted, that means m accepts x, only such patterns we are taking. Example, let's say there is a pattern called m1 hash x1, but m1 is not at all a Turing machine code. Then your then definitely this language is not having that string as a member, correct? Because we need patterns where this m should be, the first component should be Turing machine, second component should be input, and that input should be accepted by the Turing machine. Then only such patterns we are taking. Okay, it looks like we have only one pattern. It's not one pattern. It is covering infinite patterns. Who knows? But every pattern should have a property. What is that property? it should be a Turing machine code, and such Turing machine code should accept X. Then this is a language, right? Now the question is, finally you understood that this is a language, correct? Let's assume that this language's name is membership problem, okay? Because we are checking whether M accepts X or not. This is also known as membership problem. Let me ask a question in a different way. Is there any Turing machine for this membership problem? Obvious, yes. How you design? That is what universal Turing machine does, correct? So yes, I can say that this language has a Turing machine, universal Turing machine. Well, let's recall what it did. What we do is, how to design a Turing machine we do from scratch. Forget about universal Turing machine, start from fresh. Example, someone asked, can you design a Turing machine for it? Yes, I can design. How? Simple. You give me input M hash X. What is the question? If this Turing, if M accepts X, you should accept, correct? First I am writing the requirement, correct? What kind of Turing machine you want? M accepts X, then M hash X should be accepted, and other thing, anything. Then for remaining inputs, you can reject, otherwise loop, okay? That is a property of Turing machine. Can we design it? Yes. How you design it? I will tell you. Whatever the input is given, I take it into one of the tracks, okay, M hash X. Then after that, slowly, that means I am explaining my Turing machine code. I take M here, X here. Now from now onwards, I don't go into details. I say simply, I simulate M on X. If M accepts X, definitely that code, by understanding the code I can understand. If M goes to final state on X, then I go to final state and I accept the string. Which string you are accepting? X? No. If M accepts X, I am accepting M hash X, this entire pattern. So that I am designing a code for, otherwise a Turing machine for this problem, correct? When you should accept? Whenever M accepts X, I should accept M hash X. That is what I am doing. So yes, such a Turing machine is possible if you carefully plan it. Also, this Turing machine is nothing but universal Turing machine which we designed. Now, forget about this one. That means finally you realize that for this problem there is a Turing machine. Then this language, if you see this as a language, this language is dash language, then recall. Any language has a Turing machine, then we say that is a recursively enumerable language. So that's why this language is now recursively enumerable. Remember it. Now come to this problem. Understand this problem and check whether it is recursively enumerable or not. What is the problem? We have to, first of all, I explain you the language here. This language is nothing but collection of strings. Any language is collection of strings. What kind of strings? If the pattern is treated as component 1 and component 2, and component 1 is Turing machine and X is input, on input X, if Turing machine M halts, then such M hash X you should collect. Try to understand. In the world there are infinite patterns, any pattern, right? Like this, M1 hash X1, M2 hash X2, in that way. But what kind of patterns we should select in our language? If this Turing machine, sir, first of all you tell me why it should be Turing machine. What if it is not a valid Turing machine code? Reject this string. We don't want it. We want a pattern M hash X such a way that should be a valid Turing machine code. Example, let's say this is valid Turing machine code and X2 is a valid input, but M2 is not halting on X2. Sir, what is the meaning of halting? I have forgotten to tell you. Any Turing machine, we know what is the behavior, recall. It sometimes accepts a string, general Turing machine I am talking about, otherwise it rejects, sometimes it goes to loop, isn't it? Then we say that if any Turing machine accepts or rejects a string, accepts or rejects a string rather than loop, then we say that Turing machine halts. Halting means either it accepts or rejects, okay? So such state is called halting. Now come back to this problem. Example, let's say you have a Turing machine code, valid Turing machine code. X2 is a valid input, one input. Now if you simulate M2 on X2, if you run M2 on X2, then M2 is halting on X2. Okay, we have really constructed a Turing machine M2 and we gave a input X2. Let's give like this. This is Turing machine M2. and we are giving input x2 to this one. If really m2 halts, okay, then we have to collect it, m hash x. So tell me finally, what kind of strings you are collecting in this problem, second problem, also known as halting problem. In halting problem, we are collecting all possible strings where a Turing machine m halts on x. Okay, so first of all, we'll take interview of one string. My dear string, why are you in this bag? I am a member of this halting problem. What is halting problem? Really, this is one Turing machine code. This is one input. If this Turing machine halts on this input x, then this bag takes it. That means this m hash x is a member of this bag if and only if this Turing machine m halts on x. That is called halting problem. Now read it. Okay. M hash x is a collection in your bag if and only if m halts on x. Understand? Now in that way we collected lot of strings in halting problem. So it forms a language, correct? Now my question is, such a language is recursively enumerable or not is your question. How to answer it? I will tell you. Simple. If you want to know whether this language is recursively enumerable or not, only one mantra, that is construct a Turing machine. Yes, we'll try to do that. How I am going to construct a Turing machine for halting problem, you see. Simple. What is the input for halting problem? Maybe some m hash x kind of pattern, correct? Okay. What I do is just read this story, listen to this story. So I simulate m on x. If really it is a valid Turing machine code, it is a valid input, I simulate m on x. If m, now while simulating, m either will halt on x, otherwise it will be in loop. Whenever m halts on x, then I will know that, because the Turing machine m will go to t state or r state. Whenever it goes to t state or r state, then I will accept. Such a way I design my Turing machine. If it is on loop, then I also will be in loop. Okay. Now, so see this one. Is it not a Turing machine? I have constructed. See. Now really, why it accepts this kind of patterns, you see. Give a valid pattern, m hash x. Really m halts on x, we should accept it, correct? Now see, really what we are doing actually, we are running m on x, correct? If m halts on x, we are accepting. That means what? Definitely we are designing a Turing machine which halts on all these possible patterns. Let me focus on this Turing machine one more time to understand it clearly. I am designing a Turing machine such a way that whatever the input you give m hash x, see, my goal is I have to construct a Turing machine for this language. How I do, you see. First of all, I simulate m on x. Like I ask, Mr. M, do you halt on x? Because if you simulate, you will understand that. Really m says that yes, I halt on x. Then I will go to final state. I means halting Turing machine. Okay, let's say this is halting Turing machine. Otherwise, let's say Turing machine for halting problem. So it will go to accept state. To get the clarity, let me ask a question. When are you going to accept state? If m halts on x, remember it. Okay. Otherwise, what you do? I will be in loop because I don't go to accept state. Now this is a Turing machine because there is an accept button. It is not compulsory to reject something. If you have any accept state, that is automatically a Turing machine. Okay, even you don't require accept state also. Okay, you know what is a Turing machine, right? So let's begin. Why this Turing machine is going to exactly accept this language of halting problem or halting problem, we'll see. You give any input. Really m halts on x, we go to accept state. That means we are accepting this string. When are you accepting this string? M halts on x. That means finally we are accepting this language strings only. That means we constructed a Turing machine. So today you realize that m hash x where m accepts x, m hash x where m halts on x are two different problems. Correct? So otherwise two different languages. Every language has a Turing machine. This language has a Turing machine which is nothing but universal Turing machine. We have constructed it already in a neat way. Second one, this one, a Turing machine for halting problem. It is very easy to construct because already you put lot of effort on what? universal Turing machine. In the exactly same way, we can construct a halting Turing machine, otherwise a Turing machine for halting problem. Okay, so that's why I did not spend much time on this Turing machine. Very simple. Simulate M on X. If M halts on X, you also stop and accept it. Otherwise, you will be in loop. If such a way, if you design a Turing machine, then definitely it is going to accept this kind of strings only. Understand?